surprising. And so just as a little side note, so for ordinary differential equations, we get eigenvalues and eigenvectors. When you start solving partial differential equations, you get eigenfunctions. So, an interesting thing. So, I mean, I find partial differential equations more fun than ordinary differential equations. But often, sometimes when you solve partial differential equations, you end up doing some stuff, and then it involves solving ordinary differential equations, so you can solve a partial differential equation. So based on what we did with higher order homogeneous differential equations with the auxiliary equation, we know that sometimes we get repeated zeros of our auxiliary equation. So we would expect, since we have our characteristic equation for our matrix for our linear systems, we would expect that we get repeated eigenvalues sometimes in that case. So today we're going to look at the case where we have a eigenvalue with multiplicity 2. So in general, if lambda minus lambda 1 to the m is a factor of our characteristic equation, and lambda minus lambda 1 to the m plus 1 is not a factor. We say that lambda 1 is an eigenvalue with multiplicity m. I'm just going to make sure that I start this. Yes. Okay. And for some n by n matrices, it may be possible, if we have a repeated eigenvalue, to find m linearly independent eigenvectors if we have a repeated eigenvalue. So for lambda 1, and we'd say k1, k2, up to k sub n. So even though we have a repeated eigenvalue, we might be able to find linearly independent eigenvectors for that eigenvalue, and then our general solution is just is C1 K1 e to the lambda 1 t plus C2 K2 e to the lambda 1 t plus dot 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 plus C sub m K sub m e to the lambda 1 t. And because K1 through Km are linearly independent, this gives us m linearly independent solutions to our system. So in some cases, this happens where we we have a repeated eigenvalue, but we can find linearly independent eigenvectors. If we can only find one eigenvector for that eigenvalue, in that case, we can find our linearly independent solutions. So x1 is going to be k11 e to the lambda 1 t. And I'm using 1, 1 because they correspond to lambda 1. X2 is k21 t e to the lambda 1 t plus k22 e to the lambda 1 t. And we would go up to our mth. X sub m is k m1 t to the m minus 1 over m minus 1 factorial e to the lambda 1 t plus k m2 to the m minus 2 over m minus 2 factorial e to the lambda 1 t plus, and we get k m e to the lambda 1 t. And the factors of t in this solution, these solutions are analogous to the additional factors of t when we had repeated repeated roots of our auxiliary equation when we solved higher order differential equations, where we had that came from reduction of order. So we had an additional factor of t or additional factor of t squared, etc. But notice that we have that additional factor of t plus our original solution, and so we end up with some additional things here. And we can always find these k sub ij. So if we have if we have a repeated eigenvalue, we can only find one eigenvector. There is a method where we can find these other eigenvectors, given that we found one. Yes.
Yeah. What is my subscript in the last case? That
MM.
Okay.
So we're going to go through an example for each case where we can find linearly independent eigenvectors for one eigenvalue, and for the case where we can only find one eigenvector for repeated eigenvalue. And don't worry about this, all of this notation, because all of that comes out from our system of equations when we actually find our eigenvalues. So we won't have to. All of these numbers come out of our system of equations that result from our characteristic equation. Well, the point here is we can always find our linearly independent solutions, even when we can only find one eigenvector for our particular repeated eigenvalue. All right, so here's our first example. X prime equals 3, 2, 4, 2, 0, 2, 4, 2, 3, x. So our first step, I want to solve the characteristic equation a minus lambda I. Determinant is 0. So a minus lambda I, that determinant, is going to be 3 minus lambda, 2, 4, 2, 0 minus lambda, 2, 4, 2, 3 minus lambda. And we want that to equal 0. I'm going to skip some steps here. So there's some algebra in here. And we get negative lambda to the third plus 6 lambda squared plus 15 lambda plus 8 equals 0. And I'm going to say there's some more algebra here. And we get negative lambda minus 8 times lambda plus 1 squared equals 0. So our eigenvalues are lambda 1 equals 8, and lambda 2 and lambda 3 equal negative 1. So for the single eigenvalue, we can always find an eigenvector. So let's do that one. For lambda equals 8. Our system of equations becomes, let's see, 5 minus 1. So we get negative 5 k1 plus 2 k2 plus 4 k3 equals 0 from the first one. Did I do something wrong here? I did. There should be a 2 here from this. So we get 2 k1 minus lambda's 8 minus 8 k2 plus 2 k3 equals 0 from this row. And here we get 4 k1 plus 2 k2 minus 5 k3 equals 0. This one is not one of the nice systems where we can just look at our equations and pick out our eigenvector. So I'm going to do this. This is kind of the worst case scenario for a system like this. Row operations. This is one where I would say for a 3x3 system, use some technology to help you. Don't go through those row operations by hand. And I'm coming up with the way that I want to structure questions that involve this, so you don't end up having to do a bunch of 3x3 row operations by hand on a quiz or a test. Because the point is not doing row operations here. The point is doing the calculus part. Now we should be able to do row operations under duress, maybe. I looked at this one for a long time and I was like, okay, can I think of a clever way to solve this without doing row?
Multiply the top to the bottom by 2 and then just add them all. That gets rid of K2.
Oh, yeah, that could work. I did the row operations, and I ended up with negative 5 k1 plus 2 k2 plus 4 k3 equals 0. 0 k1 minus 2 k2 plus k3 equals 0. And our last row is all zeros. Oops, k2, 0, k3 equals 0. So this doesn't really give us any information. From this row, we get that k3 equals 2k2. So I just picked k2 equals 1, and k3 is 2. And then I substituted these into the first row, and I said that gives us, this was k2, k1 equals 2. Just substituted these two values into the first row to get k1 equals 2. So our first eigenvector, k1, is 2, 1, 2, corresponding to lambda equals 8. And there's a lot of stuff in between here. For lambda equals negative 1, and I'm just, again, looking at this, I'm substituting negative 1 in for lambda, and then each of these gets multiplied by k1, k2, k3. That's how I write this system of equations. So we get 4 k1 plus 2 k2 plus 4 k3 equals 0. 2 k1 plus k2 plus 2k3 equals 0. And 4k1 plus 2k2 plus 4k3 equals 0. And we see anything interesting about these equations?
They're all the same.
They're all the same. So really we have one equation with three variables. One equation with three variables does not have a unique solution. So we can get two linearly independent eigenvalues from this one equation. So I'm looking at 2k1 plus k2 plus 2k3 equals 0. We just pick k1, k2, and k3 that satisfy this, two different k1, k2, k3s that satisfy this equation that give us linearly independent vectors. So for my first one, what I chose was, for my first, I said k1 equals 1, k2 equals 0, and k3 equals negative 1. And for my second one, I said k1 equals 1, k2 equals negative 2, and k3 equals 0. So k2 is 1, 0, negative 1, and k3 is 1, negative 2, 0. And for me, in my mind, if I can get one of these, one of the components to be 0 in one of the eigenvectors, and that same component not to be 0 in the other eigenvector, that's how I'm sure that they're not scalar multiples of each other. That's, in my mind, that's my kind of insurance policy. Did I do this correctly? If I can see that, then I'm okay with that. So in this case, because we just ended up with one equation, doesn't have a unique solution, we get two linearly independent eigenvectors. And so our solution is C1, 2, 1, 2, e to the 8t for lambda equals 8, plus C2, 1, 0, negative 1, e to the negative t, plus C3, 1, negative 2, 0, e to the negative t. And because these two eigenvectors are linearly independent, it's okay that we have the same exponential there in our solution. All right, so that is the case where we can find linearly independent eigenvectors. Questions there? Okay. I would like to say that 3x3 systems are the largest ones that we do. It's the largest system of differential equations that we'll solve, but unfortunately, when we talk about undetermined coefficients, that involves systems of equations also. And one of the examples that I did involved a 4x4 system of equations for a pretty simple undetermined coefficients problem.
Is there a website that we can use that you
Wolfram Alpha will solve systems of equations.
Okay.
I just put them in, if you just put the 3 equations in, separated by commas, or 4 equations separated by commas,
Okay.
it'll solve it. Wolfram Alpha is kind of my go-to for that. It'll also find determinants, and there's an option. Yeah, let me go to the website, and I'll show you this option on the website. Or not on the website, yeah, on the, when we get there. If you do math input down here, you can put in matrices, you can put in symbolic stuff if it helps you. I usually just type it in. Just try typing things in and separating them by commas. But for a determinant, you could write, you could put the matrix and just do determinant, DET.
Okay.
And I think, if I remember right, if you put a matrix in there, it will tell you what the eigenvalues of the matrix is. So,
Wait, can you see that?
well, let's put one in, I think. 1, 3, 4. Oops, 4. Determinant, characteristic polynomial, eigenvalues, eigenvectors. So, there you go. So there's some technology that can help you. I would make sure you can find those eigenvalues and eigenvectors on your own, but you can check with Wolfram Alpha. All right, so let's look at the case where we only have one eigenvalue. I think it's kind of interesting when we put that matrix in. If you look down the list of the different things that Wolfram Alpha did,
Yeah.
it's like the more math you take, the more of those things make sense to you, and that's kind of a nice thing. Like, 2 days ago you wouldn't have known what a characteristic polynomial was and an eigenvalue and an eigenvector, and now we do. So we only have one eigenvector. We can find a second solution in the form x2 equals the eigenvector that we can find, t e to the lambda 1t, plus some other vector, p e to the lambda 1t. And I'm going to say why. This is one of those where we said, well, can we find a solution that looks like this? Let's see if it works. We substitute. Into x prime equals ax into our equation. So I'm going to say x2 prime. When I take the derivative of this thing, we get kt lambda 1 e to the lambda 1t plus kt by the product rule, plus p lambda 1 e to the lambda 1t. And if this is a solution, so a times our solution, kt e to the lambda 1t plus p e to the lambda 1t, that's going to equal this thing that we found, kt lambda 1 e to the lambda 1t plus kt plus p lambda 1 e to the lambda 1t. If that is the case, then what I'm going to do is I'm going to subtract this from both sides. So I get 0 on the right-hand side. And I'm going to factor out the t e to the lambda 1t out of all the terms that contain a t e to the lambda 1t. And I'm going to factor out an e to the lambda 1t out of all those terms. So we get ak minus lambda 1k t e to the lambda 1t plus ap minus lambda 1p minus k e to the lambda 1t equals 0. So in that case, we have to have this equal to 0 and this equal to 0. So we have a minus lambda 1 I times k equals 0. And from this, we have a minus lambda 1 I times p equals k. Well, this is how we find k1. That's the equation we've been solving that we talked about first yesterday, but we've been solving to find k1. Once we find k1, we can substitute here, use this equation, because k1 is going to be known. We can use this equation to solve for p. So we can find our one eigenvector with this equation, substitute it here to find this vector p. So it's not a difficult process. We've been doing this process. Here we just have another system of equations. So let's look at an example of this. X prime equals negative 6, 5, negative 5, 4, x. So from here, I'm going to do a minus lambda times the identity matrix. That's going to be negative 6 minus lambda, 5, negative 5, 4 minus lambda. And we want that to be 0. So I'm going to write this out. I get minus 6 minus lambda. I always write it out because I make mistakes. 4 minus lambda plus 25 equals 0. When we multiply this out and simplify, I get lambda plus 1 squared equals 0. So lambda equals negative 1. And we have a repeated eigenvalue multiplicity too. So for lambda equals negative 1, for our equation, we're going to have, I'm going to put a negative 1 here for my equation, and we get negative 5, k1 plus 5, k2 equals 0. And for the second equation, we get negative 5, k1 plus 5, k2 equals 0. And that tells us k1 equals k2. So we only get one eigenvector here. So I'm going to let k1 be 1, 1. So now we want to solve, get this one eigenvector. We're going to solve a minus lambda 1 I times p equals k1. Well, this a minus lambda 1, we're going to get the same equation, except instead of k1 and k2, k1, k2, we get p1 and p2. And instead of equals 0, equals 0, we're going to get equals 1, equals 1. So we get negative 5, p1 plus 5, p2 equals 1. And negative 5, p1 plus 5, p2 equals 1. Same equation. So what I did is I let p1 equal 0, so p2 is 1/5. There are other ways we could have done it. That's just the way I chose to do it. So our p vector is 0, 1/5. And our solution then is x equals c1 times k e to the minus t plus c2, and I get two terms in here. I get this vector, k t e to the minus t, plus this vector, 0, 1/5, e to the minus t. And there's our solution. So very similar to when we had repeated roots to our auxiliary equation, we end up with this extra term here. So the process is not difficult. We just do another system of equations to find our other vector, that vector p. We won't have to do it here, but just so we know, if you have eigenvalues with higher multiplicities, so we have if we had the same eigenvalue with higher multiplicities, for which we can only find one eigenvector, say we had an eigenvalue of multiplicity 3, and we can only find one eigenvector for that repeated eigenvalue. We use the same procedure that we just used to find our linearly independent eigenvectors. We just repeat the procedure again. So for example, with an eigenvalue multiplicity 3. And we have one eigenvector, k1. We would solve a minus lambda 1I times k equals 0. That's the equation we've been solving to find our first eigenvector. And then we would solve a minus lambda 1I times p equals k. And then we would solve a minus lambda 1I times q equals p. So we just solve this system of equations in order to find our three vectors. And the solution is x1 is c k1 e to the lambda 1 t. x2 is c2 kt e to the lambda 1 t plus p e to the lambda 1 t. That's the case that we just had. And then x sub 3 is c3 kt squared e to the lambda 1 t plus pt e to the lambda 1 t plus q e to the lambda 1 t. And our general solution would be the sum of those three.
And that would just keep going.
Yes.
Before you have KTQ.
Right, and then you'd have another term there. Yeah.
At that point, you just put whatever letter you want.
Yeah. But generally, the highest order system that we will solve is third order. And it's possible for eigenvalues of higher dimensional systems to come in various combinations. So we only talked about a few possibilities. So for example, for a 5x5 system, we could have 5 distinct eigenvalues. We could have one eigenvalue with multiplicity 2 and one eigenvalue with multiplicity 3. And those can have either linearly independent eigenvectors or not. Or various combinations of those things. So for a higher dimensional system, it gets much more complicated in terms of the possibilities and how you deal with the possibilities the same way, but there's just more variations on how the system can come out.
But you can mix and match.
Yeah, you could mix and match. You could have an eigenvalue with multiplicity 2 that have distinct eigenvectors, and an eigenvalue with multiplicity 3 that have one eigenvector, and then you have to do this process. So it just depends on the configuration of the system. And this is still section 8.2.